Okay, good afternoon. So today actually we want to start the most important part of number theory, which is called the modular arithmetic. So if you know, so far we have talked about divisibility and we learned about the division algorithm dealing with remainders and quotients. But of course, it was not very convenient to use those divisibility, especially relation, yes? Because if you remember the divisibility relation, for example, when we say A divides B, it's the simplest relation for the human brain is probably equality, yes? The equality is the simplest thing, the simplest relation between two numbers. So when I say that number A is equal to number B, then this relation is symmetric, so it means that I can write immediately B is equal to A. But this relation is not symmetric. When A divides B, here I can conclude that B is equal to A. But here I cannot conclude that B divides A. It might be somehow the case that this is yes. For example, minus 3 divides 6 divides 3. Then of course I can interchange them and write 3 divides minus 3, which is also correct. But not in general. But this relation holds in general. Yes? And then this property is something that makes it a little bit harder or counterintuitive to work with this relation. Yes? For example, if I have equality, I can multiply both sides by 2. If this is true, this is guaranteed to be true. But I cannot just multiply one side by 2. This is not true, yes? But in this case, sometimes we can, yes? If A divides B, I can simply conclude that A divides 2B. Of course, I can also conclude 2A divides 2B, but I can also conclude this, which was not the case in the equality relation. So there are some differences between natural way of thinking about the relation between two numbers and this relation. On the other hand, we should be able to talk about the remainder of divisions in number theory. So that's very important to be able to talk about the remainders of divisions. So we need to invent a new method to be able to talk about the remainders and the quotients in a more comfortable language. And that's the language of modular arithmetics, which is very close to this equality relation. So it means that you really don't need to memorize anything at all, because whatever you have, more or less, whatever you have for equalities, you can also have it for modular arithmetic. But of course, you need to get used to this kind of arithmetics that I want to describe today. Okay, so let me start the formal definition. So let me write the definition here. Let A and B be integers, and let M be a natural number greater than 1. So A and B can be any integers. So we in number theory, I told you that mainly we are talking about integers. But for this M, I want to have it a natural number and not equal to 1. M starts from 2, 3, 4, etc. We say that A is congruent to B modulo M and write it as, so I don't know which notation the book is using. I will use this notation, which is more compact. So I read it, A is congruent to B modulo M. Or sometimes the book, I think, written it in this way, or other texts sometimes you see they write it in this way. They write A is congruent to B. I don't know, for some reason they don't put it so simple. They write a pair of brackets and they write mod M. I will not use this, it's too long. Yes, so I will use this symbol and write it as A is congruent to B modulo M if M divides the left-hand side minus the right-hand side. If A minus B is divisible by M. That's it, very simple. So let me write it in. So this relation from now on, you need to translate it in the divisibility language. So this means that M divides A minus B. Of course, in the book, because they haven't introduced you this symbol, they have written it in words that A minus B is divisible by M. But now we can use this symbol because we have worked with that. So whenever you want to see if this statement is true or false, what you need to do, you need to subtract the right-hand side from the left-hand side and check if this number is divisible by this number on top. If that is true, then you say this is true. If this is not true, this is not true. Yes, as simple as that. And of course, I hope that you agree with me why we exclude 1. Why do you think we should exclude 1? Yes? Because if we want to include 1, then everything becomes trivial, yes? So I would say that A is congruent to B modulo M, modulo 1, regardless of the numbers A and B. Because whatever A and B are, the difference is always divisible by 1. So if I want to include 1, that is not an interesting thing, because this is always true. So this is why we exclude 1. And that's it. Okay, and then you see that this symbol is very similar to this. There is a reason they have written this symbol in this way, because it reminds you of the equality relation somehow. And the properties of this are very similar to the properties of equality. For example, this will be symmetric. We will see, okay? Let me write simple examples first. Number 1. For example, I can write 5 is congruent to 2 modulo 7, modulo 3. Is it true or false? If I want to see that is this a statement true or false, I would say this is true since, how should I check that? I write the right-hand side, the left-hand side, minus the right-hand side, and I ask myself, is this number divisible by this modulo or not? Modulo or not? The answer is yes. So this means that this is true. Yes, as simple as that. 5 minus 2 is divisible by 3, so you can write this in this language, in this new symbol, whatever it is. Okay, for example, what do you think about this? Number 2, I can say that 5 is congruent to minus 2 modulo 7. Is that right? So why? It is also true. Why? Since If I write the number on the left minus the number on the right, and I ask myself, is this number divisible by 7? The answer is yes. So this is also a true statement. Yes? Okay. So for example, minus 17 is congruent to 1 modulo 4. Is it true or false? So you see, I can have negative numbers for A or B, but I cannot have negative numbers for the module. The module, by definition, is a natural number greater than 1. Yes? Okay, is that true or false? What about that one? True or false? That's false, yes? Why? Since if I write the number on the left minus the number on the right, this is not divisible by 4. Yes? Because minus 17 minus 1 is minus 18, and minus 18 is not divisible by 4. So this statement is a false statement. Yes? But what about this one, for example? Minus 17 is congruent to minus 1, the same module 4. Is it true or false this time? This is true now, yes? It's true since the number on the left minus the number on the right, which has another minus sign, is divisible by 4. Is it true or false? Minus 17 minus minus 1 is minus 16. And minus 16 is divisible by 4. Yes? So this is true. Yeah, is that understandable? Let's see. So, for example, 42 is congruent to 0 modulo 6. Is that right? This is also true, yes? Why? Because if I write the number on the left minus the number on the right, this is divisible by 6. Okay, let me ask you another question. Can you give me another number instead of 0? Just change 0 to another number so that, again, the statement is true. Yes? 6, for example. Because 42 is congruent to 6 modulo 6. Why? Because 42 minus 6 is 36 and it's divisible by 6. How many numbers do you think I can put here so that this statement becomes true? How many numbers can I put instead? So 0 is one of them. It's a statement is true for 0. And then Dylan said 6. It was also true for 6. But is there any other one? Infinitely many numbers, yes? Can I put 42, by the way, there? Yes or no? Because 42 minus 42 is divisible by 6. Because 42 minus 42 is 0. And we talked about that 0 is divisible by any number, even 0. So you see that 42 is equivalent, if I want to say, to 0, is equivalent to 6, is equivalent to 42. So 42, if I want to keep the relation as equality, equality is very, very restrictive. If I write 42 and I put equality sign here and I ask you to put something instead of question mark, what can you write? Only 42. Yes? Any other thing that you put there, it is wrong. Of course, you might write 84 divided by 2, but that's another name for 42. Yes? So this means that if I want to use this relation, it is very restrictive. It is the best possible relation, But if you want to have this equality, then you have to be very limited. But if you want to work in this module 6, then 42 is 0, 42 is 6, 42 is, I don't know, any number. So 42 is even minus 7. Do you agree? No, minus 6. So 42 has another name, minus 6 as well, yes? Because 42 minus 6 is 48, and 48 is still divisible by 6. So how many names I can have for 42 if I decide to work with in the module of 6? Infinitely many names, yes? Then so that's what, and then because I have infinitely many names, I prefer to work with the smallest one. So this mentality you should develop here. We, of course, any number in any module have infinitely many names, but we prefer to work with the simplest possible one. And then you need to learn how to work to find the simplest possible one easily. As that is easy. This will come by practice. But for the time being, I want you to understand that this is true, yes? So these statements are true or false based on the definition. Okay. And by the way, I want you to be able to translate it in both sides. So most of the time, you need to have this, and you should be able to understand it as m divides a minus b. But I want you to also understand that this is the other way around as well. If someone tells you that m divides a minus b, if you want to, you can conclude this. Yes? So be careful about that. This is the both sides. You can go from left to right, right to left. Okay. But let us now discover a little bit of properties of this new relation. Okay, let us ask, is this relation symmetric? Because do you remember the main reason that we actually skipped that divisibility relation is because that relation was not symmetric. And now, is this relation a symmetric relation? What does it mean? It means that if someone tells you that this is a true statement, can you conclude that B congruent to A with the same module is also a true statement? Yes or no? If the answer to this is yes, then this means that this relation is symmetric. And then of course it would be good that I have a symmetrical relation because it becomes very similar to equality relation. So do you think this is true? Yes or no? It shouldn't be hard for you to answer immediately under 1 second. Is it true or false? It's true. Why? Because when you tell me that, let me write the answer here. So when you tell me that A is congruent to B modulo M, this means that A minus B is divisible by M. Yes? So if you really want to write everything in detail, so you will say that there exists a Q in Z such that the number on the right is the number on the left multiplied by Q. Yes? But then what can I do? I can multiply both sides of an equality by a negative sign. If I multiply by -1, this becomes positive B, this becomes negative A, this becomes negative MQ. Yes? But I don't want to have negative M because I want to have my M again, so I will absorb this negative sign into this Q. So this then implies that B minus A is M times negative Q. But what is this negative Q? What type of number is this? Q is an integer, so definitely minus Q is also an integer. So I can call it a Q, but I am guaranteed that this Q is an integer. So M multiplied by an integer is B minus A. So what is the meaning of that? It means that M divides B minus A. Yes? Okay, but I can write this as in this new language. M divides B minus A means B is congruent to A modulo M. Yes? So this relation is symmetric. So that's one property. Okay. Another very basic property of equality is that every number is equal to itself. Okay? Every number is equal to itself. Do you think that this is also true for this new relation? If I tell you that m is a natural number greater than 1 and a is an integer, are you convinced that this is always true? The answer to this is yes. Why? Because if you want to see if this is true or false, what are you supposed to do? You need to write a minus a and then ask yourself, is a minus a divisible by m? The answer is yes, because a minus m is 0 and 0 is divisible by m. So you see that this is also true. Do you remember this property was called reflexive? So this is reflexive, this is symmetric, and the other property is transitivity, yes? What was transitivity? If number A is equal to number B and number B is equal to number C, what can I conclude? I can conclude that A is equal to C. Do you think the same thing happens here for congruency here? So what I'm saying is that, do you think that if A is congruent to B in module M and B itself is congruent to some number C in the same module, of course. You see, I can have different modules here. But, so then I can conclude that A is congruent to C modulo M. If this is true, then it means that this relation is also transitive. So it means that the same properties that equality relation enjoys, this relation also enjoys. And that is easier for us to work with this, you will see, if you get used to it. And then you will get used to it, by the way, very quickly. Okay, do you think this is also true or false? Yes, I want to show that this is true. So let us prove it together. How should I prove that? How should I prove this? I will start. You are telling me that A is congruent to B modulo M. So then it means that I can conclude that M divides A minus B. You are telling me that B itself is congruent to C modulo M. What can I conclude? I can conclude the number on the left minus the number on the right is divisible by M. Yes? But I don't know, if you have forgotten, I have to do everything from scratch. But if you haven't forgotten that, I can use it. Do you remember I told you that if one number divides two numbers, then that number divides the sum of those two numbers. Do you remember? We had something like that. So I can conclude that M divides A minus B plus B minus C. I don't know, is that understandable for everyone? We had this formula. If A divides B and A divides C, I told you that this is important to remember. A divides B plus C and A divides B minus C, yes? So I am using that fact. One single number is dividing two numbers. So that number definitely divides the sum. But what happens for the sum? If I calculate the sum, this minus B and that B are gone, then what is left for me is that M divides A minus C, yes? And I told you that I expect you to be able to write this in this congruency language. What is the meaning of that? If I want to write it in this new symbol, I have a number minus another number, which is divisible by M. If I want to write it in this new language, I would say that the number that appears first is congruent to the number that appears here, modulo M. So this means that this property is also satisfied. So all three properties that we have for equality sign, I also have it for congruency sign, yes? Is that clear? But of course, we have more. and I want you to know all of them. The good news is that you don't need to memorize anything, because everything that you have for equalities you also have for congruency. So it is very fast and efficient. So for example, if I ask you, what is another property of equality? These are the main three properties: symmetry, reflexivity, and then transitivity. Okay, but can you tell me another property of equality signs, for example? A lot of things we have done. Yes, yes.
Multiply both sides with the same number.
Yes, before multiplication.
Division.
No, before
Addition.
addition. Yes, that's better if I want to keep the order. Exactly. So if A is equal to B, can I conclude A plus C is equal to B plus D? Oh, sorry, B plus C. Yes? If I know that two numbers are the same, I can add the same number to the left and to the right, and still I am sure that this equality is again true. So that's one property. Yes? Can I subtract the same number from both sides? Yes. Can I multiply, as you said? Again, yes. Can I divide? Yes, based on that C is not 0. Division is not useful for us. Why? Because we have to work with integers in number theory, so division we forget about that. So all the operations that are sensible in number theory are addition and subtraction and multiplication. Of course, in some cases you can also divide, but forget about that. In general cases, we can talk about these three things. Okay, now do you think the same thing happens here? Number 4, if A is congruent to B modulo M, do you think, and C is an integer, yes? Can I conclude that A plus C is congruent to B plus C modulo M? Can I conclude this? Can I conclude the product? The answer to all of them is yes. So that is, you see, you don't really need to remember anything. You just add something, you multiply by anything. So it's working very nice. Let me prove one of them. For example, let me for example prove this one. So you are telling me that A is congruent to B modulo M. I can immediately, by definition, conclude that M divides A minus B. So this means that there exists a Q in Z such that A minus B is M times Q. Yes? Yes. And now, you see, I want to have this product, A times C and B times C. This will motivate me to multiply this equality by C. So I am using the property of equalities. So here I can conclude that A minus B times C is equal to C times MQ. Yes? And then you multiply that, it becomes AC minus BC. But what I'm supposed to do, this is the product of three numbers. It doesn't matter how I group them, because I need to have M. So I keep M and then absorb C to the Q. But of course, this is definitely an integer, because Q is an integer, C is an integer, so CQ is an integer. So then I have the difference of two numbers is equal to M times Q. So capital Q, for example. So this means that M divides AC minus BC. But if I ask you to write this in this new language, you would write AC is congruent to BC modulo M. Yes? Is that clear? So you see, we have to prove them, because this is something completely new. So we have to convince ourselves that these are indeed the case. But the good news is that we don't need to memorize anything because it is very natural. Yes? Okay, can I have more properties for equalities? Yes? So this was good. We were able to translate this into this new language, and we were able to show that yes, this is indeed the case. Okay, let us work with two equalities. A is equal to B and C is equal to D. What can I do with these two equalities to get a new true equality? Assuming that these two are true, what can I do, for example? The very elementary things, yes? What can I do?
A plus C is
We can add them side by side, and then we can subtract them, and we can multiply them. So we want to see that, is it the case that we can do the same thing here? And the answer would be, again, yes. So let me just write this one. So number 5, I have A congruent to B modulo M, and C is congruent to D, the same module, by the way, be careful. Then I can, if I want to, I can add them side by side. I can subtract them, and I can multiply them. Yes? And I want together to prove the last one. Don't take these things for granted. You see, it's a very nice thing because everything acts very natural. But there is no reason that this should be the case. We have to prove that. So I want to prove this one. Probably this one is the hardest one. Okay? I want to convince you that if this is true and this is true, I can multiply these side by side, multiply this, and then this is still true. If this is true, I want to show you that this one is definitely true. Okay? So how can we prove that? Let us do it together. I can write here. So you are telling me that A is congruent to B, so that is the meaning. You are telling me also that C is congruent to D. I have to translate that one as well. So what does it mean? It means that the number on the left minus the number on the right is divisible by M. Okay, now I want to ask your opinion about that. What do you think I should do to prove that this is indeed the case? Any ideas? I want to have somehow the product of A and C and the product of B and D involved in my problem. So what can I do? Because usually you don't remember the theorems, I want to start it from scratch, and that's the way that is given in the book. Because I told you a lot of properties of divisibility, and if you use them, of course they are true, they are correct. But I would prefer to start everything from scratch. Okay, so you will start translating this. So this means that there exists a Q in Z, such that the right hand side is equal to M times Q. Yes. We sometimes need to talk about H and M, yes, because probably MQ and H and M, yes. Yes, might be we will have problems, yes. Okay, so A minus P is MQ, and then we have this. There exists a Q but prime, probably, in Z, such that C minus D is MQ prime. Okay, now I want to hear from you. What is your opinion? I want to conclude finally this. What do you think I should do? So in these theorems, I think this is the hardest one. It's very simple, not hard at all, but the hardest one among them. What do you think we should do? No idea? No, think logically, yes? This is the main thing. I expect you to learn this thing from me. Forget about whatever I taught you so far. You need to be able to think without your teacher. This is the main reason that you are studying. Okay? And then I told you, try to, because this is not something that I need to teach you. I told my thinking loudly. You need to look at what you want to prove, and then you see that, okay, I need to have AC, I need to have BD. If you don't have this strategy, just staring to the problem will not help. Okay? So you need to have a strategy how to continue. I hope that after Math 5 or Math specialization, you learn only this phrase from me. If you do not have a strategy, just random manipulation of algebraic manipulation will not work. Might be you are so lucky that it will work, but usually it doesn't work. So you should have a strategy. You might have a wrong strategy, but you should have a strategy. Otherwise, it's not efficient at all to just manipulate algebra randomly. Okay. So now we have a strategy. Our strategy is to make AC appear, legally of course, not just write C there and say that this AC appeared. No, you need to do something according to mathematics laws, yes? So what is your opinion now? Okay, so that is a strategy, but it's a weak strategy. I will not go for it. Why? Can you answer it yourself? That is one thing. Another thing is you get m squared somehow. Yes, you are right. So one way is to multiply them. Of course, I would say that this will also work. Okay, but forget about that. Okay, this strategy is not very efficient. So what is the next one? Okay, if I add, there is no point. If I add, AC will not appear. So you need to do something before multiplication. You will still want to have AC, but exactly because what you said, I have some extra terms, I don't want them to appear. So what should I do? Can you tell me? I'm close to writing it, yes? What should I do? No, so you put these things next to each other. You want to multiply, but you don't want to have extra terms. What I'm supposed to do? I just want to have plain AC. Yes? Yeah, exactly. So what I'm saying, if you think strategically, you can really know what to do. I want AC. I cannot ignore that because I see it in front of my face. Yes, AC should appear. And then this is the only way probably to think. It doesn't mean necessarily that this will work, but at least it's better than nothing. Yes? And I will do the same thing here. Yes? And then I multiply, and then I am happy. Why? Because AC appears. On the right hand side, what happens? BD appears. Yes? And that's good. And then, of course, when I multiply, m squared again appears. But let us see how can we... you have enough experience, by the way, here. So here, I multiply them side by side. You see, I am using this property of equality over and over again to prove properties for this new arithmetic. Okay, so then let us continue. So AC is MQ prime is m squared QQ prime. So you see, it was inevitable. I still have m squared. And then this one multiplied by that one. And this one multiplied by that one. And finally this one multiplied by that one, which is good. Now, can you solve the problem? The obstacle is m squared, but this is not the real obstacle, yes? What can I do? I can move this to the left, becomes minus BD, because I need minus, yes? If you go to scratch paper and translate this, what is the meaning of this? It means the number on the left minus the number on the right is divisible by m. So if you write this in the scratch paper, you understand that what you need is minus BD. So then you move it back on the left hand side, yes? So it becomes minus BD. And between these trees, what can I do, these three terms? I can factor an m out. So it becomes mqq prime plus qd plus bq prime. But who cares about this? You have this experience, you have enough experience about this now. So what is important for me is that it should belong to z. And it belongs, yes, because m is a natural number, q and q prime, and b and d are also integers. So this combination is definitely an integer. So what is the conclusion here? The conclusion here, m multiplied by an integer is this number. So it means that m definitely divides AC minus BD, but this we learned today. This can be written in this new language as AC is congruent to BD modulo m. Yes? Okay, but the good news is that who cares about this? We can just, you don't need to memorize anything because it is very natural. Yes? What more? We can also raise to powers, yes, the equality. For example, if I have 6, if I have A equals to B, I can raise it to power n. Of course, between numbers, this n can also be any kind of numbers, even negative ones. But in number theory, we have to have those things for integers. So I would say that if A is congruent to B modulo m, and if n is a natural number, so I emphasize here, then of course I can raise it to power n. Yes? Of course, if you want to prove this, you can use this idea n times, yes? Because if when I say that A is congruent to B modulo m, it means that you can write it m n times. For example, you can write it 2 times. Let me write it 3 times. Because when you tell me this is true, it means this one is the copy of that one. This is also true. This is also true. And then I learned that I can multiply them side by side. Yes? And then the name of this is a to the 3 and this is b to the 3. So you see that I can prove that a to the 3 is congruent to b to the 3. But if you want to prove it rigorously, we have to learn mathematical induction, or we need to learn a little bit about some identities. But that is the idea. Yes. So you see, you really don't need to be worried about anything, except you are not allowed to divide, you are not allowed to take the root. And that the answer is clear, because when you divide, the answers might not be in the integers. Even if the answers are in the integers, you have to be careful. That is not sometimes true. Yes, for example, this is very important to learn. So you might think that I will be allowed to divide if the dividend, if the quotient is an integer. Even in that case, this is not true. So for example, let me see if I can bring you a counterexample. So let me write like this. Do you think this is true or false? This statement is true, yes? 24 minus 6 is 18, and 18 is divisible by that module 6 there. But let us divide everything by 6. If I divide this by 6, what will happen? It becomes 4. It's still an integer. And I divide this by 6, it becomes 1. But this is false. Yes? So you see 4 minus 1 is 3, and 3 is not divisible by 6. So don't think that if the quotient is an integer, I am allowed to divide. No, for division you need another theorem, which is not in the book, so let us ignore about that. But what I want you to know is that, of course, if I ask you to divide by 10, you immediately realize this is not possible, because when you divide this by 10, it becomes 2.4, and then you realize that this is not valid when I have a non-integer number. But the point is that even if you have an integer at the end, the answer might not be true. Be careful. So you are not allowed to divide. Okay? So be careful. In equality, we are allowed to divide if the number is not 0. But here we are not allowed to divide under any circumstances unless you know the exact theorem. Okay? So forget about division. And of course the nth root, if I give you this, then there is no guarantee that the nth root of this is congruent to the nth root. But raising to power is possible. Is that clear? So you see that working with this is actually very simple. Let us do some exercises. So let me see if I have missed something. Okay, so for example, let us see how this will work in practice. This is a very important example, a simple example, but this is actually the spirit of these calculations. So you need to learn this example very good. So, let me write the title of the example, Simplify each number to a positive integer less than the given module. So simplify each number to a positive integer less than the given module. So what I will tell you what does it mean. So here, number 1, I want you to simplify 5 multiplied by 64 to the power of 12 plus 15 times 17 in module 7. Okay, so let me tell you what does it mean. So this is actually a big number, and then no calculator is allowed for these parts, so you need to do it without calculator. And by the way, if you want to use calculator, I can make it 1200. Then even calculator will not be able to give you the right answer. Yes, because that would be so huge that you cannot. So it is possible to make questions that even if you have calculator available, you cannot use calculator. Okay? So this is why I'm just saying that try to learn what is going on here. So if I want to simplify, let me start simplifying this and then tell you how to do it more efficiently. But try to follow my steps only. You will see what happens at the end. Don't resist, okay, why should I do this, why should I do that, yes? So what I do, I don't care about 5. And the reason is that 5 is already a small number. And it is already smaller than my module. Okay, so this is why I don't care about 5. Let me care about 64. But 64 for me is 1. This is the importance of this modular arithmetic. I can throw it away and put 1. Why? Because in module 7 there is no difference between 64 and 1. 64 is congruent to 1 modulo 7. Why? Because 64 minus 1 is 63 and 63 is divisible by 7. So as far as I care about module 7, there is no difference for me between 64 and 1. Yes? First of all, I don't want to get you confused. Is that true or false? This is true, yes? Now, am I allowed to multiply both sides by 5? This is true, yes? Are you doubting about this? This is true. I can multiply it by 5. So I can multiply by 5 this one. Oh, sorry. Before multiplying by 5, I can raise it to power 12. Yes? It becomes 64 to power 12 is congruent to 1 to power 12. Yes? We just showed that if I have a true congruency, I can raise both sides to any natural power. And because the power here was 12, I decided to raise it to power 12. Yes? But which one is easier to calculate? 64 to power 12, I really need a calculator, but 1 to the power of 12 is just 1 to the power of 12. Yes? It's just 1. So this becomes this. So, as far as I am working in this module, 64 to power 12 is just 1 for me. Is that understandable? Okay, now let us go to the other one. So what can I write for 15? Can you tell me something small, a good number? I want you to follow your instincts. Yes? So 15, what can I write for 15 in module 7? A very good number. Of course, I can write infinitely many numbers, but which one you choose, the best one? The best one. Which one is the best? Because we are humans, we understand what we are talking about. Yes? 1. Agree? 15 is nothing except 1. Because 15 minus 1 is 14. 14 is divisible by 7. So this is 14. Okay. What can I write for 17? A better number than 17. What can I write? What can I write? 3, yes?
Yes.
Yeah, I can write 3. Of course, 3 is better than 17. It's smaller. And 1 is better than 15. But I want to have 15 times 17. Am I allowed to multiply side by side? We just learned that, yes. So what I do, I multiply side by side. But then 1 times 3 is easy. It becomes just... So this I don't know. Let us keep it. Of course, this is not hard, but let us keep it. But this becomes 3. Yes? Do you agree or not? So what I have written here and what I have written here are true. But I didn't even calculate this big number. If you ask me, if I calculate this number to power 12, multiplying this by itself 12 times and subtract 1 from it, is it guaranteed that that number is divisible by 6? I can surely say yes, because I proved this. Yes, but I didn't calculate that. Is that understandable? And that is the power of this. Now, we also learned that if I have two congruencies in the same module, I can add them side by side. Yes? So I will add this one to this one. So it's not complete yet. I forgot this factor of 5 here. So it means that I have to multiply by 5 again. But that's also simple. I did it now. And then let me take this box away from this and put the box here. And then what I do, I add this one to this one, then I am done. So it becomes 5 times 64 to the power of 12 plus this number, 15 times 17, is congruent to this number plus that number, which is 5 plus 3, module 7. And then finally, this becomes 8. This becomes exactly the number that the problem gave to me. So this becomes 5 multiplied by 64 to the power of 12 plus 15 times 17 is congruent to what? 8 in the module 7. Yes? Is that clear? Okay, this is done. Which one is easier to work? This number or that number? Of course, 8 is easier for us to work, and we didn't use even calculator. But this is not acceptable in the problem because I have written simplify. There is a reason why I have mentioned this. Simplify each number to a positive integer less than the given module. So that is 8 is a positive integer, but it's still not smaller than the module. Okay, but what can I write for this? 8 itself is what? Can you tell me a good number here? 1. Yes? Because 8 minus 1 is 7. 7 is divisible by 7. And then I would say this number is congruent to this. This number itself is congruent to 1. So comparing them, what can I conclude? 5 times 64 to the power of 12 plus 15 times 17 is congruent to 1 module 7. So this is the simplified version of that. Yes? But the good news is that I can do it much faster and more efficient. I will tell you. Okay, but if I want to tell you that method, you will not learn that everything that I told you is needed here. So let me just review. I started from this one. This I will explain why I started from here. Yes? But you agree with me this is true. And then from this step, I am allowed to go to this step based on one of the theorems that I can raise to both sides to some power. And from here, I am allowed to conclude this. Why? Because I am allowed to multiply both sides. Yes. So this is a true statement. This is a true statement, definitely. I am using mathematical rules. So what I get is definitely a true statement. And then I use these two and multiply them side by side. But I just showed that this is possible. Then I am sure that this is definitely a true statement. Then I have this one and that one. I told you that you can add them side by side. So definitely this one is also a true one. Yes? And then when I came here and I wrote this one and I compared them using transitivity. This one is congruent to this and this one is congruent to this. So I can conclude that this is true. Is that right? Yes or no? So you see that all the rules that I explained is being used here. Yes? But if you ask me to solve this problem, I will never do it so long. And I want you to learn to do it fast. Okay? But doing it fast have this problem that you might don't understand what you're doing, but you can do it. Okay. So here, if I want to solve that problem, I would write this. And then I would write 7 immediately. And what I do, I go to my expression and I look at all the bases. Yes, the numbers which appears as a base, not an exponent. And I will try to simplify these bases. That's the only thing that you need to do. Yes. Okay. For 5 is relatively small number. Even though I can change it to something else, but why should I? For example, for 5, I can write minus 2. Agree? Why 5 is minus 2? This you need to be quick in this understanding. Why 5 is minus 2? Because 5 minus minus 2 is 7, and 7 is divisible by 7. So another name for 5 is minus 2. But because 5 is already manageable, so let us not change it, yes? So I would write 5. But 64 is not a good number. Yes, it's actually beyond my module. And I will try to find a good number for it. What is the meaning of a good number? Here, I can, instead of 64, I can, for example, write 8. Do you agree, first of all, with this statement? 64 and 8 are the same. Why? Because 64 minus 8 is 56, and 56 is divisible by 7. I can clean this and write 8. Yes, I can clean 64 and write 8. But that is for me again the same problem. Of course, 64 to power 12 is much larger than this number. But if I want to do it with hand, there is no difference for me between 8 to power 12 and of course 64 to power 12. Here I also need to multiply 8 by itself 12 times, which is still time consuming. So this is why you need to be a little bit patient, even though if you write this, this is totally correct, but it is not that efficient. Because 8 to power 12 for calculation with hand is still a big number. Yes? So here you have to be patient and ask yourself, can I find a smaller number so that if I replace 64 with that number, raising it to power 12 becomes easier? Okay? And there are 3 numbers that you need to always think if possible. Sometimes it is not possible. 3 numbers that you can easily raise to high powers. What are those 3 numbers? There are 3, yes?
-1, 0, and 1.
Yes, these are the 3 numbers that you can, so if I say -1 to power 1 million, you don't have any problems, yes? It becomes 1. So these 3 numbers are very important, but sometimes it is not possible, of course. If I, instead of 64, if I have given you 65, what is the lowest number that you can choose? In that case, it would be 2. But 2 to the power of 12 is still problematic. Then I will teach you what to do with those, okay? But for the time being, try to think, can you do better? And I hope that you agree with me. Instead of 64, what can I write? 1 in this case. Yes or no? And now go. Plus, instead of 15, I just write 1. Because 15 minus 1 is 14, and 14 is divisible by 7. Instead of 17, what can I write? After 15, I have the product. I put product. Instead of 17, what can I write? I can write infinitely many, but which one is better? As you said before, 3. Yes? And then you calculate this. 1 to power 12 is 1. Times 5 is 5. And this is 3. And that's 5 plus 3 is 8. That's quite okay. This is a good number, but because the problem has asked you to write it as a positive integer smaller than the module, because 8 is not still smaller than the module, according to the problem I have to continue. But of course, what is another name for 8? Which has that property 1. And then I know. Yes? And the reason that I am asking you to do it like this, don't stop here, because we will see. If I ask you what is the remainder of this number by 7, the answer is 1. That is the whole point. So do you remember we suffered a little bit to find the remainders? Okay, but now if I have a so big number and I ask you what is the remainder of this big number by 7, the answer is 1. And I will prove it for you why this is the case. So this is why I want you to learn, even though 8 is a good number, but I want you to make this 8 smaller than 7. Do you remember? Division algorithm. The remainder cannot be greater than the divisor. It should be smaller than the divisor. Yes? Okay, let me give you another example. It seems a little bit mysterious. I don't know. I see some question marks on your heads. But so let me see what can you do with this one. We can do this together, okay? So can you try to simplify this together? So 5 to the power of 15 multiplied by 26 to the power of 6 plus, so I have written 18 factorials here, but you haven't studied. I don't know, so let me, what is the module? The module is 3. Okay, so I would write 18 to the power of 1000, okay? And then I would write module 3. Okay, so help me to do that. If you want to simplify this huge number in module 3, what I'm supposed to do, I will try to write this and then I put a 3 here. What I care about are the numbers that appear as a base. These are the numbers that I am allowed to change. Okay? And then, I think you know what to do then. What do you write for 5? -1 is better. 2 is also correct. If you write 2, that is 100% true. But 2 to the power of 15, still I have some problems, yes? 2 to the power of 15 is still a big number. So you shouldn't be in a hurry, especially in the exam questions, because might be if you go a little bit higher, just wait a little bit and check, you might find the proper number. Unless this problem is hard, then I will teach you how to do that. But for this one, I prefer to write -1, even though 2 is also right. So I would write -1, but I would put 15 there. Okay, let me stop. Is there any one of you don't understand why I replace 5 with -1 in this modular 3? The answer is because 5 minus -1 is 6, and 6 is divisible by 3. The people who answered I should write 2, they are also correct, because 5 minus 2 is 3, and 3 is divisible by 3. But if I put 2 here, I have to raise 2 to power 15, which is hard. But if I put -1 here, I have to raise -1 to power 15, which is simple. So this is why I prefer to write -1 instead of writing 2. Okay, let us go forward. What can I write for 26? -1 again, yes? So you see you are learning. -1 to power 6. Yes? What can I write for 18 here?
0.
0. 0 is the best choice. 0. I want to make sure that you really understand what's going on. Do you understand? Whatever base you have, you can take it away and put any number that you like, of course, in that module. But you need to not be in a hurry to choose any number that is you immediately understand. You need to find the best choice if possible. But do I have problems with calculating this? Not at all. Yes, this becomes congruent. Be careful to write this all the time. -1 to power 15 is -1. Multiplied. -1 to power 6 is +1. 0 to power 1000 is 0. And then calculate this simple number. So, -1 times 1 is -1, plus 0 is -1. Yes? Of course, this is completely correct, but according to the problem, I want to simplify each number to a positive integer smaller than the given module. So it means because of this expression, I have to continue one more step. Okay, can you tell me what should I write? I want to have positive number and smaller than the module itself. What should I have? Yeah, I know this is a little bit hard in the beginning, but you get used to it immediately. What's that number? Give me a number so that this number minus that number is divisible by 3, and that number is positive and is smaller than 3. Yes? 2, yes, 2. Thank you. Yes, because -1 minus 2 is -3. -3 is divisible by 3. Yes? This is the reason that I spend a lot of time about divisibility and algorithm division. It will come later. So I hope that you can immediately understand that this one minus that one is divisible by 3. So the answer to this question is 2. So instead of working with this huge number, if you only care about module 3, you can just work with 2 and be happy. Yes? Any questions? Is there something, I don't know, I feel that there is something wrong, that you don't understand something. Yes, is it true or not? Is that understandable, everything? Yes or no? Okay. Yes?
Could you write instead of 2 minus 1?
Instead of 2 minus 1,
0 divided by 3.
0 divided by? Why? No, what is your question again?
Is it possible to say that? Could you have minus 1 instead of 2?
Yes, if this is not written, you can stop at minus 1. And now I want to tell you why I insist you to write this. Because so you need to learn to write it as a positive number smaller than 3. If there is no constraint like that, if you stop here, that's okay for me. But usually, if I don't say something like this, people can have different answers in the exam. Yes? Minus 1 is true, I don't know, the other, so 2 is true, and then you can write other negative numbers, other positive numbers. So if I want to have it a unique number, I have to limit your choices somehow. And the reason that I really want you to limit your choices to this particular choice is the reason that I want to talk right now. Okay? So let us talk a little bit about this. I give you two numbers, A and B, and I say that these two numbers, this is very, very important. Actually, this is the core of this lesson. And I say that this is true. A and B are integers. M is a natural number greater than or equal to 2. And I tell you that this is true. My claim is that if I divide A by M, and if I divide B by M, the remainders are the same. This is a very important thing I want you to understand. If two numbers are congruent in some module, if I divide the left-hand side by this module and I find the remainder and put it in a box, and I divide the right-hand side by the module and put it in a box, then these numbers in the boxes are the same. But why? So my claim is that, this is my claim. If, this is a theorem. If A is this, and then the remainders of the divisions of A and B by M are equal. Of course, this is if and only if, but the other one is so trivial that I didn't even mention. I will come back to it if you have problems here. But that is not trivial. Sorry, if the remainders, okay? This is not trivial. So by the way, let us, for example, check. If I have, I don't know, if I have a little bit non-trivial example. So I would write 65 is divisible by, so is congruent to, let me make it simple. 50, so let me write it simple. So 15 and 10. Do you agree with this? 65 is congruent to 15 in the module 10, yes? Why? Because 65 minus 15 is 50, and 50 is divisible by 10. Now, what this theorem claims that if you divide this by 10 and find the remainder, what is the remainder of the division of 65 by 10? So you divide 65 by 10. What is your quotient? Your quotient is 6. What is your remainder? Is 5. And if you do the same thing here, you divide 15 by 10. What is the quotient? Is 1. What is the remainder? Again, 5. So the remainders are always the same. Okay? But this is, I want to prove that this is not a coincidence. This is always the case. Let us see why. Okay, so when you say that A is congruent to B modulo M, what does it mean? It means that M divides A minus B. Yes? Okay, now let me divide A by M. Division algorithm tells me that there exists a unique Q and a unique R. Let me write them Q1 and R1 in Z such that A is equal to M times Q1 plus R1, but R1 is somewhere between 0 and M. Do I need absolute value for M here in this case? Because if you remember, the division algorithm has an absolute value there. But do I need absolute value here? No, because by definition M is a positive integer, so I don't need that absolute value. And then there exists another unique pair, so let me call them Q sub 2 and R sub 2 in Z, such that B is equal to MQ2 plus R2, and R2 is between 0 and M. Yes? So you told me that this is true. I concluded this is true by definition. And then you told me that I have a number A and a number M. I use division algorithm to write this. You gave me B and M. Again, I use the division algorithm to write this. Okay? My claim is that R1 has to be equal to R2. So let me write this claim here. Transparently here. Claim. I want to show that R1 is equal to R2. This is my claim. I want to prove this for you. There is no guarantee that R1 and R2 should be the same, but I want to show that under this condition, R1 and R2 has to be the same. Yes? Okay, so can you help me to do that? You see, I know that M minus B is divisible by M, and I know that these two equality holds. If you ask me, do you know anything about Q1, R1, Q2, R2, I would say no, because I don't know A and B, I don't know M. But at least I know something about R1 and R2. Yes? This is the only thing that I have. Okay, can you help me to prove, I am claiming that R1 is equal to R2, and I want to show that this is indeed the case. How can I do that? Okay, so this is a little bit hard. It's a little bit abstract, but I would say that I want to claim that I want to show that R1 is equal to R2. If you don't believe, so it means that R1 is not equal to R2. So then it means that either R1 is smaller than R2 or the other way around. Okay, so if not, then R1 is less than R2 or R2 is less than R1. Yes? I want to show that they are the same. If you don't agree with me, then you have to agree with this one or that one. Yes? Okay, let us, for example, concentrate here. If R1 is less than R2. Yes? Okay, but you see that this is my assumption. I am certain about this part. So I have to have A minus B available. So this motivates me to subtract these two. So when I subtract them, it becomes a minus b, then it becomes mq1 plus r1 minus mq2 plus r2. Yes? Then what happens? This becomes m, and then this becomes q1 minus q2, and then I will have plus r1 minus r2. Okay, so if you don't mind, let me assume that the other way around. Yeah, that's correct. So let me write R2 is smaller than R1. The other way around, I need to subtract the other way around. Okay. But if R1 and R2 are between 0 and m, can you tell me what is the interval for R1 and R2? I know that R1 and R2 are two numbers between 0 and m. For example, here is 0, here is m. They are integer numbers. R1 is greater than R2, so R2 is somewhere here, an integer. R1 is somewhere here, an integer. Yes? Can you tell me can this number be larger than m? R1 and R2 are in this area. Can R1 minus R2 be beyond m? Or can it be below 0? You see, below 0 it cannot happen because I am assuming that R1 is greater than R2. So R1 minus R2 is definitely positive. But can this number be larger than m? The answer is no, because R1 and R2 are smaller than m. So how is that possible? When I subtract them, it becomes bigger than m. So this means that R1 minus R2, what is R1 minus R2? Is a number greater than 0 and smaller than m. Now look, a minus b is equal to m. Instead of this one, I write capital Q. And then plus, instead of this one, I write capital R. What I know about R is that R is between 0 and m. Yes? Now I ask you this question. Can I say that R is the remainder of a minus b by m? Yes. Why? Because that is the division algorithm. You see, a minus b is m times a integer plus another integer, so that this integer is between 0 and m. So R is the remainder. But this is contradiction. Why? Because the remainder is supposed to be 0. Yes? Understandable? So this is a little bit hard, I agree. This is why the book has just mentioned it. But this is not above your knowledge. You should be able to understand this. So the book is using it without giving you the reason. But the reason is actually the way that I mentioned it. So what I'm saying is that if this is true, and if I assume that R1 and R2 are not equal, then I will understand that the remainder of a minus b by m is a positive number, not 0. But this is contradiction because I am assuming that a minus b is divisible by m. So this means that these two remainders has to be the same. Of course, if I want to make it right, I need to consider the other case as well. Okay. Okay, I know that you are a little bit tired. I will repeat this part, not the proof. If you want to learn the proof, you can watch the video. But next time, I will start from here, which is the main topic of this lesson. And then definitely a lot of questions of that type will be in the exam. Okay, so that will be the main part of this lesson here, modular arithmetic. Okay, thank you.